Alrighty, so we're doing something totally different in chemistry today. We're going back to our third unit, which is on solutions, acids, and bases. And we're going to kind of just recover a few of the things that we covered right before that school lockdown, or rather school shutdown, I should say, that occurred back in late November. The topic today that we're learning is one that I think you guys were pretty keen on, at least when we were first learning it. But again, it is really important to go back over it because we were really not in the right mind space when we first learned it. We're learning F and P. No, just kidding. We're learning pH and pOH, right? So pH is something that's hopefully pretty familiar to you. pOH was something that was totally brand new, but we're going to get going here. So today's plan, we're reviewing some acids and bases concepts from before. We're going to look at neutralization reactions. Psych, never mind. I just took that out of here right before I started the video. We're not doing that. We're going to look at behavior of water. Psych, we're not going to look at that either. What we are only looking at today is relating pH to the concentration of hydronium ions. Remember that was H3O positive in solution. And we're also going to look at pOH, which is another way of describing how acidic or basic something is. Now, just a reminder, this is in the solutions, Unit C, Part 2 booklet. That's the one that has that comic of Calvin from Calvin and Hobbes in the front of it. Make sure you have that handy. We've already filled in the notes for this, but at the end of the lesson, the practice questions I'm going to get you to do have to do exactly with this. Anyway, let's get going. So aqueous solutions, entities in water that form hydronium ions have a huge range of the amount of hydronium ions in solution, in other words, the concentration. This leads to the creation of the pH scale. If we want to just back up here, let me remind you that the amount of hydronium that is in something is really what dictates how acidic something is, right? So hydronium, once again, that's H3O positive, or sometimes you can even just call it H positive. That's hydrogen ion concentration, but these are directly related. We'll talk about that in a second. The more concentration you have of hydronium ions, the more acidic something is. Acidic concentrations are just anything that has more than 1 times 10 to the negative 7 moles per liter of hydronium ions. On the other hand, basic solutions are anything with less than 1 times 10 to the negative 7 moles per liter of hydronium ions. So again, these hydronium ions, these H3O positive ions, or in other words, these H positive ions, they're the ones that actually dictate how acidic something is. So if we're going to talk about the power of hydrogen and the power of hydroxide, so in other words, the pH and the pOH, the pH scale, of course, just measures how acidic or basic something is from 0 to 14. A pH of 7 is neutral. A pH less than 7, as backwards as this sound, is acidic. And a pH greater than 7 is basic. So the power of hydrogen basically means the lower the number, the more powerful hydrogen is. And again, that does sound backwards, but you have to realize, at least in a second, that it's because that number represents a negative exponent. So things kind of go backwards with that. Anyway. The pOH scale is basically the same thing, just backwards. The pOH scale measures also how acidic or basic something is. It also ranges from 0 to 14. Water, just like with pH, water has a pOH of 7. It is totally neutral. But the pOH scale is just the opposite of the pH scale and is used to determine the amounts of hydroxide ion concentration. So that's OH negative. At room temperature, the pOH of a solution can be obtained approximately by subtracting the pH of the solution from 14. We'll do a few examples of that right here. So calculate the pOH of the following solutions. If we knew that the pH of ammonia cleaner was 11.3, to find the pOH, we just have to go 14 minus 11.3. And I'm pretty sure, I don't think I need to touch a calculator on this one. I'm pretty sure that would be 2.7. So 2.7 would be the pOH of ammonia cleaner. So 2.7 pOH means fundamentally the same thing as a pH of 11.3. If we had salad dressing, on the other hand, it has a pH of 2.65. I remember us talking about this and being like, would it really? Like, that sounds like a really low pH. Like, that's some really acidic salad dressing. But anyway, if that's the pH of that, we find the pOH just by going 14 minus 2.65, which I believe would be 11.35, I think, as your pOH. Again, it's just you subtract your pH from 14 to get your pOH. That's about it. I'm going to skip these other two because you know what? I think you guys get it. Next question here, what scale of pOH would turn litmus paper red? Always go back to what you know on these ones. Red litmus paper means acid. An acid is something that has a pH that is less than 7. So if we're going to reverse that for a pOH, the scale of pOH that would turn litmus paper red would be a pOH greater than 7, right? So it's backwards. Even though a number bigger than 7 would usually mean basic for pH, a number bigger than 7 for pOH actually means acidic. So again, understanding pH. pH is a measure of the amount of hydronium ions or hydrogen ions in solution. Since this range is huge, it's been set up to increase by 10 times each successive step up. In mathematics, we call this a logarithm or relationship with, we should say, which increases or decreases exponentially. So what this basically means is something that has a pH of 3 versus something that has a pH of 4. This guy is 10 times more acidic than this one. Now, if we had a pH of 5 thrown in here, that would mean 4 is 10 times more acidic than 5. And since it's 10 times to get here, times another 10 times to get here, this difference is a 100 times difference. Because 10 times difference here, and then 10 times more difference here. 10 times 10 is, of course, 100. Here's a bit of a logarithmic scale if you're to graph this as a function of pH versus hydrogen ion concentration. Again, it just decreases exponentially. You don't have to worry about this too much. So here's something else we'll do. Each step of the pH scale is 10 times the ion concentration, just like we said. How much does the H positive concentration change from a pH of 3 to a pH of 5? So if we're going from 3 to 5, how much does the hydrogen ion concentration change? Well, we kind of just did an example like this. It's definitely going to be 100 times, but since we're going from 3 to 5, we should say it's 100 times less, because H positive dictates how acidic something is. Since we are moving away from a very high, or rather I should say a very low pH, which is a high concentration, it's going to be less. Now, if we have a pH of 9 to a pH of 6, this is a difference of 3, so it's going to be 1,000 times. And since we're going from 9 to 6, we're getting more acidic, so it's going to be 1,000 times more. What about how much does the OH concentration change from a pOH of 7 to a pOH of 9? So this time around, we're dealing with a pOH. Since it's going from 7 to 9, that's actually meaning that our hydroxide is getting weaker. The difference between 7 and 9, of course, is 2. So it's going to be 100 times, because there's 2 zeros, 100 times. And it's getting less, the power of hydrogen is actually getting less. I know how backwards that always sounds, but it is what it is. So it'll be 100 times less is what I'm getting at. All right, making decent time so far. We're going to keep running through. Again, we've already got all this in our note package. You can fill in if you somehow missed it before. Now here's something really important. Converting from H3O positive concentration to pH and vice versa. Just an FYI, when you see something in these square brackets, like H positive in square brackets or H3O positive in square brackets, that just means the concentration, right? And that's always measured in moles per liter. So a hydronium ion forms when water and H positive react by the following equation. So H2O plus H positive becomes H3O positive. For our purposes in Chemistry 20, we're just going to assume that this and this are the exact same thing, okay? So there's a weird formula, and you might want to jot this down somewhere so it's a little bit more available for you other than in your note package. pH equals negative log of H3O positive aqueous. So that just means take the negative log of your hydronium ion concentration, and that'll tell you what your pH is. Now, in case you're wondering what this log log button thing is, log is something that is on your calculator. If you have a TI-83 or a TI-84, it's actually right next to the 7 button. All you have to do is just punch that in your calculator, and then you're all good to go. So here's the first example. What is the pH of a solution that has a concentration of 1.45 times 10 to the negative 3 moles per liter of H3O positive aqueous? So this right here means the concentration. We're given the actual number for the concentration. We're looking for the pH. So we just have to say pH equals negative log of the H3O positive concentration, which is 1.45 times 10 to the negative 3. There's not really an easy way to do this in your head, so you have no choice but to use a calculator on this one. So if I'm going to bust out my calculator right now here, let's see, negative log 1.45 times 10 to the negative 3. That is going to give me, and you know what, we'll just round 3 sig digs because that seems to be what's in the question. pH equals 2.84. So 2.84 would be the pH if this was your H3O positive concentration. Fascinating, I know, totally exciting. Example 2, you guys should be able to try this one. Come on, so what is the pH? Oh wait, no, you won't be able to try this one. Oh, see there I was roasting you. There I was, ooh, this is actually trickier one than we thought. What is the pH of a solution that has a concentration of 4.45 times 10 to the negative 2 moles per liter of nitric acid? That's the reason why this one's tricky. That's why I went right? It is not giving us the concentration of our H3O positive. It's giving us the concentration of the nitric acid. Now, why does that matter, you might ask? Well, let's write out the formula for nitric acid. Nitric acid is hydrogen nitrate. Nitrate is NO3, so this is going to be HNO3. And you might remember from quite a while ago that acids will often dissociate or ionize into separate pieces. This is going to be one of those cases where HNO3 is actually going to split apart into H positive and NO3 negative, as long as it was all contained within an aqueous solution. It'll split apart into its ions. Now, what I want you to notice on this one is when we did this, there technically is a coefficient of 1 in front of all of this because it already is balanced. H positive and NO3 negative, they have to exist just in one part. But if there were some other numbers in here, we'd have to start putting coefficients in, is what I'm trying to say. Since there's a 1 in front of all these numbers, though, the concentration of HNO3 is going to be the same as the concentration of your hydrogen. And remember from before, H positive concentration is like the same thing as H3O positive concentration, at very least for the purposes of our course. So psych again on me. Once again, this is about as simple as the other one. You just had to double check something before you got started with it. Remember, pH equals negative log of your H3O positive concentration. So this right here, because it's the same one part of each one, we can just use that same number there. So it'll be pH equals negative log of 4.45 times 10 to the negative 2. And again, you have no choice on these ones but to use your calculator because there's not really an easy way of calculating these without one. 4.45 times 10 to the negative 2. That is going to give you to 3 sig digs, 1.35. So quite a high, or rather I should say quite a low pH, a very high concentration of acid in that. So yeah, there you go. It's just a matter of using that formula. All right, here's another one. What is the pH of a solution that has a concentration of 3.75 times 10 to the negative 4 moles per liter of acetic acid? Well, acetic acid is hydrogen acetate, or in other words, you could write this out as CH3C, that's supposed to be 3, CH3COOH. This will actually split apart into CH3COO negative and a single H positive. And what do you know? Once again, the coefficients in front of all these is 1. So the concentration here of this guy is actually going to be the same as the concentration of your hydrogen ions. So you might as well just say pH equals negative log of 3.75 times 10 to the negative 4. Throw that in your calculator real quick. Let's see here, negative log 3.75 times 10 to the negative 4. And bingo, bango, bongo, 3.43. That's your pH. No big deal. Awesome. All right, so we've been doing all these questions. You might be thinking, oh, okay, cool, pH. Well, what about pOH? Well, I mean, one thing you could do with pOH is you could solve for your pH and then just subtract it away from 14 and then you're good to go. But there's got to be a better way. There's got to be another way we can calculate that. Well, there is. Well, sort of. Never mind, I totally was wrong. No, I guess another thing we could say is how would we go the other way? Oops. Yeah, so we're going to go the other way here. I'm not going to re-record that. We're going the other way here. pOH, yeah, you know what? Just do the pOH, the same thing I just said here. Just subtract it away from 14. Or another thing, you know what? I will just close this off. pOH, the formula for that is the same. It's negative log, except this time it's of your OH negative concentration. Boom, spoiler, done. All right. The other thing we can say is, how do we go the other way around? H3O positive concentration is 10 to the negative pH. Honestly, I think that's an easier equation. You don't have to muddle around with log or anything. So if you're asked, what is the H3O positive in brackets, which means the concentration of your hydronium ions in solution, of a solution that is a pH of 3.6, well, it's just going to be H3O positive in brackets equals 10 to the negative 3.6. That's about it, right? So 10 to the negative 3.6 is going to equal a really messy number, but again, watch your sig digs here. We've got 2 sig digs going on. So that answer is going to equal 2.5 times 10 to the negative 4. And it's really important that we include our units on this one as well. It's going to be moles per liter. That's it. That's all there is to it. So make sure you have this formula available somewhere too, because it is a really important one. And I mean, this one here that I totally just gave you here, that's also pretty important too. Maybe you want that one. Last example here, it's example 5. How many grams of HCl were dissolved in 1 liter of water if the solution has a pH of 1.91? Well, again, we know the pH, and then we know we're dissolving hydrogen chloride, which is HCl, you know, hydrochloric acid in water. Hydrochloric acid splits apart into ions in the easiest way possible. It just becomes H positive and Cl negative. Just like the other ones we've seen, there's only a 1 in front of all these, so we don't have to worry about different concentrations. But if we find how much concentration of our H positive that we have here, that would tell us our concentration of HCl. We know how many liters we have, and therefore we could find how many moles we have. And from the moles, we could find how many grams we have. So I'll go back here. We're looking for grams of this guy. The only way to get grams out of an equation like this is to use moles. Well, moles can come out of a concentration, which comes out of pH. So it's this huge roundabout way of doing it. Anyway, let's get going with this. Remember, the H3O positive concentration is equal to 10 to the negative pH. We know the pH here, so we might as well say our H positive concentration, that's the same thing as H3O positive, equals 10 to the negative 1.91. Throw that in your calculator, 10 to the negative 1.91. Gives us, and that actually gives us a full decimal here. So you know what, I'll even leave it as a whole thing, 0.01230.26877, and that would be moles per liter. This right here is the concentration of your hydrogen ions. Maybe I shouldn't waste space like that. Let's see, hydrogen ions, that's the concentration right there. But because there's a 1 in front of all this, this is also your concentration of HCl. Now this is in moles per liter, so you could say 0.0123026877 moles per liter equals some number of moles over some number of liters. Well, we know it's actually 1 liter, so it's over 1 liter. Well, guess what? To get moles by itself, you just got to times by 1 liter on both sides. Let's save ourselves the trouble of this. We're going to realize timesing by 1 does nothing. So I'm just going to erase this and just recognize that my number of moles is 0.0123026877 moles. But we're not done yet. We're trying to find our number of grams. Grams has to come from our molar mass, more specifically our molar mass of HCl. The molar mass of HCl is just 1 hydrogen plus 1 chlorine. Well, hydrogen is 1.01 plus chlorine, which is 35.45. So that would give us a total molar mass of HCl of being 36.46 grams per mole. Set this equal to some number of grams. That's what we're looking for, divided by some number of moles, which is 0.01230268777. And then last thing we got to do here, one last final step here, is multiply it over to the other side. So multiply by 36.46. And you are going to have to 1 sig dig. Holy smokes, 1 sig dig. That is unfortunate. But you know what, whatever, it is what it is. To 1 sig dig, you're going to have x equals 0.4 grams. And that is 1 sig dig, because remember, leading zeros do not count. So 0.4 grams is 1 sig dig. And there we are. We're all done. Look at that. Yay, see, that wasn't too bad. Hopefully that made some sense and wasn't just a total rambling, incoherent mass of nonsense. But if it was, here's the good news. I'm available on Zoom. You can come find me. Just come talk to me and I will help you out with whatever you need. But for practice, what I need you to get done is questions 1 to 9 at the end of the Solutions Unit C Part 2 booklet. Now, most of those questions there have the answer attached. I'm pretty sure those answers are correct. But again, if you get something a little iffy, come back to the Zoom and ask. Anyway, best of luck, guys.